The only reason you can see a complete picture on a television screen is because the eye can be fooled. The picture you are seeing is a mixture of electronics, chemistry, and the physiology of the human eye. To explain how a TV picture is formed, it's convenient to start with the familiar newspaper, as we can use this to explain the basic principles which make television work. First, we'll look at the newspaper photograph and examine it closely. It's made up of many small black dots on a white background. You can pick up a paper and see this for yourself. In the very light parts of the picture there are no dots. In the dark regions the dots are very close and may even be touching. In the intervening shades of grey, which make up the tonal quality, the dots are spaced apart from each other. The wider the spacing, the lighter the picture. The closer the spacing, the darker the picture. Here is a complete grayscale made up from dots printed with different spacings on sheets of paper. By zooming in close we can see them quite clearly. But if these dots are made small enough and the eye is far enough away, then the eye cannot distinguish one dot from the other. We say the eye cannot resolve the dots. And so the picture appears as continuous shades between white and black. So what we learn from the newspaper photograph is that a large number of well-placed dots can deceive the eye into thinking it sees a continuous picture, with a complete range of greys running from black to white. The other thing we can learn from a newspaper is how we assimilate the large amount of information on a printed page. We do not take in this large amount of information all at once. Our eyes start at the top left-hand corner of a column. They zip back from the right side to the left and continue this scanning from left all the way to right with fast return as we read the page in horizontal lines, while allowing the eyes to simultaneously move down to the next line. In this way we assimilate the large amount of information on the page which is presented to our eyes all at once. Our eyes break the total message into small parts and assimilate each small part in an orderly manner. These two ideas, breaking a large mass of information into small parts and assimilating it part by part, as in reading, and presenting a large amount of information in small separate parts, as in the photograph, are both very important. They're important because these are the two principles used to make television work. There's no mechanical or electrical way to transmit a large amount of information from place to place in one go. The only way to do it is to break the mass of information into small sections and transmit each section one at a time. Let's look at two common examples where this process is used. The first is the simple teletype. A whole story is broken down into words which are then typed a single letter at a time in an orderly manner. The words are then sent, letter by letter, over a transmission line to the receiving teletype. This builds the total message in the same way, a letter at a time, until the message is complete. The other example which demonstrates these principles is the method used to transmit a wire photo from place to place. It's worth looking at a simplified method of doing this before we discuss television. To transmit a photograph by wire, it is wrapped around a drum which rotates in front of a photoelectric cell. The cell then views small sections only of the picture as the drum rotates. In other words, the cell is made to scan the picture just as the eye scans a page. The cell converts the reflected light from the photo into an electric signal. This signal, which is now an analog representation of the photograph, is amplified and sent over a wire to the receiver. This signal is very important. We say much about it later. At the receiver, a photographic film is wrapped around a similar drum which rotates at the same speed as the transmitter drum. The current now varies the intensity of a small lamp which is focused onto the film. This exposes the film, a section at a time, and produces a photographic copy of the original. To get a better idea of what is happening in this process, imagine your eyes are the photoelectric cell scanning a picture. This is how the picture would look. Only one small section would be seen at a time. Each of these small sections is what is converted to the electric current. In practice, the sections would be much smaller than these, and many more would be used in each line. It would also be much faster than this, but we're keeping it slow for illustration purposes. In fact, the actual scanning process would look continuous, smoothly dissecting the picture into very small sections which are necessary if the picture contains fine detail. When the picture sections are assembled together at the receiver, it again appears to be a near continuous scanning process, smoothly building a picture a row at a time until it's complete. Now we know the principle of how a picture can be transmitted from place to place by an electric current. We need to know how to make the reproduced or copied picture usable. For this, three things are necessary. The sections viewed by the cell must be small enough and enough of them used so that the tiny detailed parts of the picture can be faithfully reproduced. The cell must be able to distinguish between the various tones in the original and convert these to an electric signal. In other words, we must have a tonal range or a grayscale with sufficient grays in it. The picture must be scanned in a definite pattern. This ensures every part of the picture is transmitted and ensures the copy is built properly. The first 2 points can be demonstrated quite easily. This is a copy of a picture. The sections are too large and the area viewed has been averaged to a level of grey somewhere between black and white. 4 levels of grey have been used. All this shows is a rough outline formed by the picture sections with no detail at all. The sections are so large the reproduction is useless. Here the sections are made a quarter the size of the previous. Only 2 levels of grey have been used, black and white. The formless shape has become a face, but all detail and even some edges are lost. By adding the other 2 levels of grey, the picture is improved, but it is still of limited quality. By reducing section size again by 4, the details begin to stand out, as shown in this black and white copy, and the face can actually become recognizable. By adding in the 2 remaining greys, the result is almost acceptable. Just defocus your eyes and look. By reducing the sections to minute size, they can reproduce fine detail quite accurately, and with as few as 4 greys, a usable picture results. Examining this copy closely shows the very small sections. It also shows the ability of the eye to provide whatever is missing. This is an important psychological and physiological point which helps in the reconstruction of a copy. This shows the effect of sufficiently small sections to make the picture appear continuous. Although only black and white have been used, the result is an excellent outline of all the details. Compare this with this earlier picture, where 4 levels of grey were used, but the section size was too large. From this we can see that section size is of prime importance to detail. No matter how many levels of grey are used, if the sections are too large, detail will be lost. But what this lacks is the ability to distinguish one detail from another. For this, we need to distinguish between their levels of brightness and darkness. In other words, we need the greys. When we add sufficient levels of grey to the small sections, then the details are separated and the copy takes on the necessary tonal quality to give a faithful reproduction of the original. To summarize then, we must break the picture into sections as small as possible to be able to distinguish or resolve the outline of the detail. And we must use enough levels of grey to be able to distinguish one detail from another by its relative brightness. To show the full effect of using sections which are too large, look at what is happening here, where the sections used is the same size as these patterns shown. The reflected light is converted to an average grey, and this alone is what will be produced. So each of the very different detail patterns seen here will end up as a simple grey section on the copy. So section size is important to both final tonal quality as well as detail. The only way to improve the copy is to use smaller sections of the original and more levels of grey between black and white. Usable pictures can be produced with 4 levels of grey, but for good quality we need about 10 between black and white. The actual number of dots or picture sections to use we will cover later, as this has several conflicting factors, especially when discussing television. The third point, which is important to television, is how the picture is broken down into the sections and how they are reconstructed to form a copy. A definite scanning pattern must be used, and the same pattern must be used at both transmitter and receiver. When the transmitter photocell is looking at this point, then the receiver lamp must be illuminating a corresponding point. This will build a copy in the same pattern as the original is dissected. If they are out of step, as here, then instead of an accurate copy, we will produce this, or something even worse. Thus, to ensure the picture is correctly reproduced, the cell and the lamp must be synchronized in their scanning movements. So, to summarize the process of transmitting a picture by wire, there are 3 important factors we must consider. First, we must break the picture into small sections. Ideally, these should be as small as possible, and we should use as many as possible so that we can distinguish the fine details in the original. Second, we must look at each section in turn, and we must do it in an orderly, synchronized manner, just as the eye reads words. Third, the cell used to scan the sections must be able to distinguish between the levels of grey in the picture. This allows us to separate one detail from another. Each of these 3 ideas are essential to reproducing a good quality picture by electrical means, and they are the basic principles of television. Each will be discussed again as we explain how television works. With the 3 ideas of a picture formed from a pattern of dots or sections, scanning these in an orderly manner, and having a grayscale, we can now turn our attention to how a television picture is formed. Like a newspaper or wire photo, a television picture is also a mosaic of dots, but on a glass screen instead of a paper page. First, we will see how the dots are formed on the screen, and then see how they are used to make a picture. A television screen is the front end of a cathode ray tube. We will not examine closely how this works, but you should know what a television screen is. A cathode ray tube is a shaped glass tube, and it has 3 main sections. At one end there is an electron gun, then the accelerating and focusing section, and the image section or screen, which is a phosphor coating on the inside of the glass front plate. The electron gun produces electrons which are accelerated and focused into a narrow, fast-moving beam. When the beam hits the phosphor, it causes it to glow, producing a small bright dot on the face of the tube. This is shown here on the face of this oscilloscope. Compare the size of this dot to the size of the screen. It's small enough to reproduce fine detail and reproduce it as a quality picture. As the cathode ray tube produces only 1 dot, this dot must be used many times over to create the illusion of many dots. This is accomplished by moving the dot from place to place. The dot is made to move horizontally from left to right so that it traces out a line across the screen. As it moves faster, the eye cannot follow it satisfactorily, and eventually it looks like a complete line. It's the persistence of vision of the human eye which produces this effect, and allows itself to be fooled into thinking it sees a line instead of a fast-moving dot. If the dot is moved downwards slightly on each successive horizontal sweep, it will trace out several lines. Here we have 8 lines. When the dot completes the bottom line, it returns to the start of the first line and starts scanning all over again. These lines will appear simultaneous if the dot travels fast enough. Obviously, 8 lines is not enough to create the illusion of a complete picture. Here, 64 lines are used. They cover the whole screen and give the appearance of being simultaneous. But it is one single dot, moving fast enough to fool the eye. To get differences between light and dark and create a grayscale on the screen, the dot is made to glow brightly, dimly, or not at all. We vary the intensity of the dot by varying the strength of the beam from the electron gun. A bright dot is obtained by turning the beam full on, a dim dot by turning it down, and no dot appears on the screen if the beam is cut off. Here we're starting with no beam on the left of the screen and increasing it in steps until it's at its maximum on the right. The result is the simple 4-step grayscale shown. The quality and number of grays on the screen is a function of the chemistry of the phosphor coating and is a very complex subject. So now we can compare the newspaper photo and the television picture formed on a cathode ray tube. The newspaper photograph is many dots of varying density presented simultaneously. The television picture is one dot of varying brightness which is moved over the screen in lines fast enough to fool the eye. Up to now we've been using an oscilloscope to show the dot and how it is moved. Now look at the TV screen. If we look closely at the TV screen, we can see the lines formed by the single dot. If we stand back a short distance, the lines appear to merge together to form an unbroken picture. A complete array of lines is called a raster. With no picture, it is known as an unmodulated raster. With a picture, it's called a modulated raster. The grays in a television screen are produced by varying the strength of the beam. The beam is varied by an electric signal applied to the electron gun. This signal originates in the television camera, and so now we will turn our attention to this. We now need to look at how the original scene to be televised is converted into the electric signal which is applied to the monitor. In other words, how does the television camera work? In the wire photo, a single cell was used to slowly scan across a photograph. The earliest successful television camera was a modification of this idea. It was a mechanical system which contained a rotating disc with slots or lenses. As the disc rotated, each slot or lens divided the scene into strips and looked at only a small part of each strip at a time. These were focused in turn onto the cell. A system using this principle was devised by Bell Labs in the United States and Baird in Britain, and television programs were actually transmitted over the air with this. It had many problems, but showed television was possible. Modern television began when an electronic method was devised. The electronic tube originally used has undergone many refinements, but the basic principle is unchanged. The early tubes were called iconoscopes. Later there were various types of orthicons, image dissectors, and a low-quality tube called a vidicon. Because it was so much simpler and smaller than the other tubes, the vidicon was very attractive, but it was not until about 1960 that it became a high-quality tube good enough for broadcast. The plumbicon is a special type of vidicon. As almost all tubes in use are now plumbicons or vidicons, we will concentrate on how the vidicon works. The vidicon is a straight glass tube. The light from the scene to be televised is focused on the flat glass plate at one end. Inside the tube, the glass has a transparent conductive coating, and this is covered with a material whose electrical resistance is dependent upon the amount of light falling on it. This is called the target. Both the target and the conductive backing are connected to an external conductive metal ring. Instead of using a movable photoelectric cell or a rotating wheel with lenses, the target is scanned by an electron beam. The other end of the vidicon tube contains an electron gun. This produces a beam of electrons which are formed into a fine beam and aimed at the target, just as in the picture tube. When the beam hits the target, it completes a simple electric circuit. If a bright light falls on the surface of the tube, the resistance of the target will be low. If a dim light or no light falls on the face, the target resistance is high. Many chemicals exhibit this effect, and it's quite common. If the light level varies, then the target will change its resistance to follow the level of the light. What is important is that the target does not have a single overall resistance value. The separate molecules of the target adopt their own individual resistance value corresponding to the light falling on them. This allows the complete target to have a resistance pattern across its surface, which is a representation of the image focused upon it. The beam is now adjusted to a constant strength and it scans the target. The only variable in this simple circuit is the resistance of the individual target element on which the beam lands. So as the beam moves from element to element, a different value of resistance is introduced into the circuit. This causes the output voltage to vary. The action is similar to the simple resistor divider circuit. As the top resistor is varied, then the output voltage will vary. So as the beam moves from element to element of the target, or as the light level of a particular element changes, then the output voltage will change accordingly. In this way, the scene focused on the target is converted to an electric signal. By making the beam scan the target in an orderly manner, the output voltage will be an orderly and organized representation of the scene being viewed. This voltage is very small, so it is amplified in the camera to about 0.7 volts, and this is used to produce a picture on the monitor. At this point, we can now review the process by which a television picture is made. The scene to be transmitted is focused onto the target of the camera tube. The target is scanned by an electron beam. The beam has a very narrow cross-section, so it effectively splits the image of the scene into very small parts. As the beam scans across the target in horizontal lines, it effectively reads the image. The brightness of each section of the image determines the level of the output voltage. The electric signal produced is now fed to the monitor, where it varies the strength of the beam in the tube. This varying narrow beam is made to scan the tube face, where it causes the screen face to glow. The brightness of the glow depends upon the strength of the beam, and so in effect the beam writes a glowing picture on the tube face. In both camera and picture tube, the beam has a very narrow cross-sectional area, and so it splits the picture into small enough sections to reproduce the fine detail. And both beams scan in the same pattern, ensuring the complete picture is correctly reproduced. So the combination of electronic image dissection in the camera and electronic picture display on the tube can produce a high-quality reproduction of an original scene. We have seen how a picture focused on the target of a Vidicon tube is scanned and dissected by the electron beam of that tube, and how another beam in a cathode ray tube scans the phosphor surface, causing it to glow and produce a visible image. What we must now look at is how the two beams scan the target and the picture face. Obviously, both beams must be at the same point in the picture at the same time. They must be synchronized. This is the same situation as with the cell and the lamp in the wire photograph. If the two beams scan in step, then a faithful copy will result. If they are out of step, then the copy will be of no use. A definite scanning pattern is desirable for two main reasons. It will ensure that the whole picture area is scanned and sections will not be left out, and it will ensure that any camera will work with any monitor. A definite scanning pattern has been chosen as the standard throughout the television industry, and as we shall see, it is the most important subject to the whole of a television system. Many scanning patterns can be used, and several have been tried. However, the pattern universally chosen is the same as we showed earlier. The electronic beam is made to move in near horizontal lines across the screen. Looking at the cathode ray tube, the beam starts in the top left-hand corner, scans across to the right-hand side of the screen. It then traces out similar horizontal lines, one below the other, until the screen is filled with these lines. So both an horizontal and a vertical movement of the dot is required. The reasons for this scanning system is partly psychological. Most stationary lines that we see are vertical: buildings, furniture, people we are talking to, etc. But most movement is horizontal: walking, cars, aeroplanes, ships, etc. Using horizontal lines just suits the eye better. We'll now look at this pattern of horizontal lines in more detail. The dot or beam starts scanning the picture at the top left-hand corner of the screen. It travels across the screen to the right-hand side. This left-to-right travel carries and displays the picture information, and it is called an active line or scan. When it reaches the right-hand side, it's quickly returned to the left-hand side, so that it can trace out another active line below the first one. This right-to-left sweep does not carry picture information, and it is called a retrace or a flyback. So the actual scanning pattern is near horizontal lines as shown here. It is not like this. To prevent the retrace carrying picture information, the beam in both camera and picture tube is cut off during the retrace period. We say it is blanked. So the many horizontal lines displaying the picture have an invisible retrace line between them. Blanking the beam is very important in television and is an essential part of the television system. To get a complete picture on the television screen, we need a vertical movement so that the successive horizontal lines will scan across the screen, one below the other, until they fill the screen. When the lines reach the bottom of the picture, the beam is returned to the top to begin scanning again, and repeat the whole pattern. To do this, we also need a vertical retrace period. The vertical times are much longer than the horizontal times. In one vertical down scan, there are many horizontal scans. When the beam gets to the bottom and writes the last line, it is not returned to the top in one simple sweep, as here. The time it takes to return to the top is equal to several horizontal scans, and the beam is allowed to move horizontally while retracing to the top. So its vertical retrace path looks like this. This also is blanked. So, like the horizontal flyback lines, the vertical flyback lines also carry no video information. There are several reasons for using this long flyback time. It has the advantage that it can place the beam much more accurately at its starting point than would be possible by returning it in one single movement. Returning the beam back to the top in one simple movement produces the effect shown here. There is much horizontal tearing and picture instability. By preserving the horizontal movement during the vertical retrace, the active lines at the top become much more even, and this helps to prevent tearing and results in a much more stable picture. The horizontal and vertical movements continue all the while the picture is displayed on the screen, and they are independent of the video information in the picture. So now, let us examine what makes the beam move and scan the screen. The beams in the camera and monitor tubes are moved horizontally and vertically by magnetic fields produced by coils around the neck of the tubes. One set of coils is used for horizontal movement, another set is used for vertical movement. The magnetic fields are produced by currents in the coils, and both fields and currents are varied by applying voltages to the coils. The coils are wound in yokes, as seen here. The beams are synchronized or kept in step horizontally by using the same signal to simultaneously drive the scanning coils around the camera tube and the picture tube. The actual signal is generated in an oscillator. The vertical movement is produced in a similar manner. Another oscillator produces a signal which is simultaneously fed to both sets of vertical coils around the tube and the picture tube. The horizontal coils produce the left to right scan of the beam and then the fast retrace. The vertical coils produce the slow downward movement of the beam until it reaches the bottom, and then the faster vertical retrace to the top. The combined effect of the two coils is to move the beam in a continual horizontal scanning pattern and to make each successive line appear under the previous one. When the screen has been completely covered, the beam returns to the top and starts all over again. The nature of the electric signals fed to the coils will now be covered. Let us look at the horizontal first. The signal from the horizontal oscillator is a series of pulses. Due to the inductive nature of the coils, these will produce currents in the coils which rise and fall linearly with time. The currents produce magnetic fields around the coils and make the coils behave like magnets. As the current changes direction, the magnets reverse polarity. The magnetic field deflects the electron beam in the tube, so the coil is oriented around the neck of the tube to a position where it will deflect the beam horizontally. As it changes polarity, it deflects the beam the other way. The magnitude of the current will determine how wide the deflection is. The speed of the deflection is determined by how long it takes the current to rise or fall to its maximum and minimum levels. This is how the retrace is made much faster than the visible active left-to-right scan. The vertical movement is produced in exactly the same way. Another set of coils are used, and these are fed a signal from the vertical oscillator. This produces slow downward movement followed by a fast vertical retrace. We said earlier that the beam is blanked during the horizontal and vertical retrace periods. Blanking the beam is very easily accomplished. The signal from both oscillators to the coils is also fed to a blanking circuit. The only time this circuit operates is during the retrace period. The output of this circuit controls the operation of the electron gun. In the camera, the beam is set to a constant strength, and in the picture tube, the beam strength is varied by the incoming video signal. During the active scan time, the blanking circuit does not interfere with the beam. But during the retrace time, the blanking circuit simply switches the electron gun off and no beam is produced. What we have not covered is the number of lines that will be displayed on the screen before the beam is returned to the top. Obviously, the more lines we use, then the more complete and continuous the picture will look, as it means we are looking at smaller sections of the original to create a higher quality copy on the screen. The exact number of lines to use in one vertical sweep and the exact relationship between the horizontal and vertical sweeps is quite a complex subject which we will return to later. Now that we have examined the principles of how a television picture is formed by a camera and a monitor, we should take a brief look at the electrical signal which connects the two. This signal is an analog representation of the scene, and it is used by the tube to form an image on the screen. So let us now look more closely at how the camera forms this electrical signal. As the beam in the camera scans the target, it completes a simple voltage divider circuit. If a dark section is scanned, the target resistance is high and the output voltage is near the battery positive volts. If a light section is scanned, the target resistance is low and the voltage output is close to the battery negative voltage. During retrace, when the beam is cut off, the voltage will be at the positive voltage of the battery. This very low voltage is amplified to about 0.7 volts before it is sent from the camera to the monitor and other equipment. In this process it is inverted, so the blacks are represented by a low voltage, the whites are represented by a high voltage, and the retrace is represented by the lowest output voltage. Assume the picture to be televised is vertical black and white stripes. As the beam crosses the black stripe, a low output voltage appears from the camera. As it crosses the white, a high output voltage will appear. So as one line is completed, the output varies between a high and a low voltage. When retrace occurs, the output will be a little less than the black level, and note that the retrace is much shorter than the active time. This pattern repeats as successive lines are scanned. Here we are showing two lines. They are being shown on a special oscilloscope used in a television studio to observe and check the television signal. It is called a waveform monitor. The trace is showing the two horizontal lines of video, and the blanking period can be easily identified between them. We can also show many lines instead of just two. And here we see two complete sets of lines on a screen, with the vertical blanking between them. And this is the waveform of a typical television scene. The main use for the waveform monitor is to check the level of the video signal. It ensures that the bright sections of the picture do not cause excessive signal voltage, and ensures the dark regions are also at the correct level. This is the scene we are checking, which has a good mixture of light and dark regions. The waveform monitor is used extensively in television studios to check the video signal, and further uses will be described later. We now come to a subject of great importance to the television signal and the overall television system. We've seen how the beams in the camera and monitor must scan the target and tube face in exactly the same pattern and be very tightly aligned in both position and time. We say they must be synchronized. This is achieved by driving the coils around them simultaneously from a horizontal and vertical oscillator. In a studio, it's possible to feed the cameras and monitors from central oscillators and thus ensure this coincidence of scanning. But, most important of all, this is obviously impossible for home viewing. Each home with a television set would need at least 3 lines to connect it to the studio. To change station, all 3 lines would have to be changed. To transmit the television picture over the air would require 3 separate transmitters, one each for horizontal, vertical and video. And each home TV set would be a combination of 3 receivers. A system like this would be difficult to implement and maintain and be excessively costly. Obviously, a better method is needed. Fortunately, it was easily found. The outputs of the vertical and horizontal oscillators were simply added to the video signal before it left the camera. So the video signal changed from this to this. These pulses added to the video information are called synchronizing pulses, or sync pulses for short. Without the sync pulses, it is called a non-composite video signal. With the sync pulses, the video signal is called a composite video signal. This new composite video signal is then fed into the monitors, and the horizontal and vertical connections to the monitors are dropped. So now only one connection is needed between the camera and the monitor. This composite video signal can be fed to a single transmitter, thus making television transmission to the home possible. We now have the situation where the signal from the camera to the monitor is a complete video signal consisting of both video and synchronizing information. The composite signal must now perform the dual functions of providing both the picture and the scans in the monitor. To do this, when it enters the monitor, it is fed to 2 circuits simultaneously. One is a video amplifier. This amplifies the signal and feeds it to the cathode ray tube, where it modulates the beam. The video part of the signal varies the brightness of the beam and writes the picture on the tube face. The sync part ensures the beam is cut off or blanked during the retrace period. The other circuit removes the video information and leaves only the sync pulses. This circuit is called a sync stripper or a sync separator. The sync pulses are then further separated into their original horizontal and vertical pulses. These are now fed to their respective coils around the tube, and the beam is scanned exactly as in the camera. The sync pulses are also fed to a blanking circuit to ensure that the beam is cut off during retrace. Let us now examine the sync signal in a little more detail. The horizontal pulses are much narrower than the vertical pulses, and they occur at a much faster rate. The scope is showing horizontal pulses on the lower trace and a vertical pulse at the top. We must show many horizontal pulses before we can show 2 vertical pulses. If we combine these 2 pulses, the result looks like this. Now, both the horizontal and vertical pulses occur at the same time the beam is blanked. So when the pulses are added to the video signal, they are added at the time of the blanking period. This is what a few horizontal line periods look like. If we close these up, we can see the vertical blanking time as well as many horizontal blanking times. The video signal with horizontal and vertical sync pulses added can be viewed on the waveform monitor. We can view at the horizontal rate and at the vertical rate. The sync pulses are adjusted to be 0.3 volts in amplitude, while the video is 0.7 volts. The horizontal and vertical pulses are generated by separate oscillators, but these are usually contained in the same box or piece of equipment. Also included is the circuit which combines these into the sync signal. This piece of equipment is called the sync generator. In the small industrial or educational cameras, a simple sync generator will be an integral part of the camera. This allows small, inexpensive cameras to be operated without any additional equipment. This is important if it is to be used in difficult or inaccessible places. Now, only one cable is needed to connect the camera to the monitor. If the camera is to be used in a studio with other cameras, then all the camera beams must be scanning synchronously. If they were not, we would have problems every time we cut or dissolved from one camera to another. To ensure all the beams are scanning synchronously, a separate single sync generator is used, and this feeds all the cameras with horizontal, vertical and sync. In summary, we see that the common composite video signal is a composite of 2 main parts, the video information and the synchronizing information. And the synchronizing pulses are a combination of both horizontal and vertical pulses. The horizontal and vertical pulses are used by the monitor to synchronize its beam with the beam in the camera so that the picture tube will present the same scene viewed by the camera. This very basic scanning and synchronizing arrangement will work very well in a simple television system. But for several reasons, in a modern practical television system, such as used in broadcast, industry and education, an improved synchronizing signal is used. Why the improved sync signal is necessary is explained later. So, in conclusion, we can summarize and review the basic principles of television. To start, the original scene must be dissected into very small sections, similar to the newspaper photograph. In a camera, this is done with an electron beam, which scans an image focused on the target of the camera tube. This produces a video signal. Coils around the neck of the tube are used to make the beam move in its scanning pattern. And the same oscillator circuits add sync pulses to the video signal. The composite video signal enters a monitor or television set. Here, the sync is separated from the video signal. The video and sync are used to vary the brightness of the beam, and so produce a picture on the face of the tube. The sync pulses are used to drive the coils around the tube neck, which cause the beam to scan the face of the tube. The result is an electronic picture written on the screen, which is a faithful reproduction of the original.